So now we're going to start the last lesson of Unit 1, which is going to talk about reaction mechanisms. So far we've talked about how to monitor a reaction rate, how to increase a rate of reaction, and looking at the enthalpy change and activation energy of different reactions, including their potential energy diagrams. It's a lot. And now what we're going to do is look at reaction mechanisms, which is how reactions actually happen. So you might be surprised to know that chemical reactions do not usually happen in one single perfect step. So for example, if you look at this reaction here of hydrogen bromide with oxygen, so gaseous hydrogen bromide with oxygen, forming water and bromine gas or bromide gas, it doesn't happen that four of these hydrogen bromide gas molecules and one of the oxygen diatomic oxygens just collide and magic happens. Instead, what happens is that there's a series of smaller steps called a reaction mechanism. So really what happens is only a few particles will collide at a time, and each step will have its own energy requirements and its own speed. So if we look at this reaction of the oxidation of gaseous hydrogen bromide, the mechanism steps or the elementary processes would be as follows. Step 1, you would have a single hydrogen bromide gas meeting with diatomic oxygen, and it would form HOOBr. Now this reaction is incredibly slow, right? And so we would call it the rate determining step, meaning it's the slowest part of the entire reaction. And then what you'd have is this HOOBr combining with another hydrogen bromide gas and forming two HOBr gases. Now, this is a very fast reaction, so it would be happening. So as soon as those HOOBrs are produced, they're looking to react with the hydrogen bromide gas, right? It's a quicker reaction, it has a lower activation energy, and it's going to happen quicker. Then these two HOBRs is going to combine with the last two hydrogen bromides to form the two waters and the two bromide gases. So the net overall reaction is what's going to be left if you add all these three steps together, canceling out any species that appear on both sides. So for example, if you look at this reaction, you've got HBr plus HBr plus two HBrs forms those four HBrs that we knew, or hydrogen bromides, that we knew were part of our reactants. And then we've got the one oxygen. So we've got the 1, 2, 3, 4 hydrogen bromide gases combining with the one oxygen to produce two waters and two of these bromide gases. But what about everything else? Well, everything else you're going to notice is produced and then used. So for example, this HOOBr is produced in step 1 and then consumed in step 2. These two HOBRs is produced in step 2 and consumed in step 3. So they cancel out. They wouldn't be part of your overall reaction. It's kind of like writing a net ionic equation where if the ions occur on the left and the right, you cancel them out, right? And so what ends up happening is that these are reaction intermediates. They are things that are formed in one step, so they're a product in one step, and then used up in a later step. It doesn't have to be the next step, but in a later step as a reactant. So they do not appear in the net reaction. They may be unstable or short-lived, but sometimes they can exist on their own for a while. So if you have a really slow reaction mechanism, maybe the HOOBr is there for a while before it's going to combine with a hydrogen bromide gas. The reaction intermediates for this reaction mechanism is that HOOBr and the HOBr. The other part that is not included in this reaction mechanism, but is also an important thing, is that there would be activated complexes formed for each of these steps. So each of these steps has its own potential energy diagram, which we'll be looking at later. But all I want to describe to you right now is that each of these steps would have its own activation energy, and if there's sufficient energy for a successful collision, would form its own activated complex. Now, the activated complex are found just by adding up all the atoms involved in the two reacting molecules, including coefficients and subscripts, and the order doesn't matter. So, for example, if we look in this first step, right, I'm just going to erase all my crossing out. If we look in this first step, there's one H, one Br, and an O2. 1H, 1Br, and an O2 is my activated complex in step 1. In step 2, I've got a hydrogen and another hydrogen, so I've got two hydrogens. I've got a bromine and a bromine, so I have two bromines, and then I have two oxygens. So my activated complex would be H2Br2O2, right? There's two hydrogens, two bromines, and two oxygens, and it wouldn't matter if you wrote this as H2O2Br2. It's the fact that all of these things are coming together to break bonds, form new bonds, or rearrange the atoms. So in step 3, I've added in some coefficients, and I just want to make sure you know how to include them. So you have two of these HOBRs, and so you'd have two hydrogens and another two hydrogens to make H4. You'd have two bromines plus another two bromines to make Br4, and then you have two oxygens, which would make an O2. So those are my 3 activated complexes for this 3-step reaction mechanism. Each step you can call a mechanism step, or you can call an elementary process. So some key takeaways is that most reactions occur in multiple steps. There's very few reactions that are simple enough just to happen in one. Each step is part of an entire reaction mechanism. The reaction intermediates are things that cancel out, and they do not appear in the overall equation. The slow step often controls the reaction rate, so we call it the rate determining step. And if you wanted to speed up a reaction, you have to speed up the slow step. If you speed up one of the fast steps, you're not going to change the overall reaction rate. And the other part, just to assure you, reaction mechanisms are not something that you're going to be asked to come up with. They are deduced through much study and research. Sometimes it's taken years to figure out a certain reaction mechanism. So you are going to be given reaction mechanisms and asked for overall reactions, or they're going to give you an overall reaction and ask you for maybe a missing step. I find these kind of like puzzles. You either like them or you don't like them, but if you like puzzles, you'll probably enjoy this. So the first thing we're going to do is just practice one simple reaction mechanism where we come up with the overall reaction and we identify any reaction intermediates and all of the activated complexes. So the first thing I'm going to do is go through and cancel out any species that are on the left and the right. So I'm going to look first at this 2s on the left. There is no 2s on the right, so it doesn't cancel out. I've got these two O2s on the left. There's no O2s on the right, so nothing's going to cancel out. I have this SO2 on the left and an SO2 on the right, so I have two of them, and each of them are going to cancel out. All right, sorry. The downside of filming videos at home. My kids just got home and distracted me. So where were we? So S was on the left, didn't appear on the right. O2 was on the left, didn't appear on the right. SO2 was on the right, appeared again on the left, right? And then the SO3 is a product and appears again as a reactant. Water doesn't cancel out, and either does this sulfuric acid. So what are we left with? Well, my overall reaction would be the two S's. Then I have two O2s plus another one O2. So I have three O2s plus the two waters forms these two sulfuric acids. So this would be my overall reaction. And then let's identify our reaction intermediates. So our reaction intermediates would be the things that we crossed out. So the SO2, which was a product and then consumed as a reactant, and then the SO3, which was a product and then consumed as a reactant. And then lastly, my activated complexes. So for step 1, my activated complex would be S2O4 because there's two S's with the coefficient and then two O2s, which would make it O4. My activated complex for step 2 would be two S's, so S2. O4 plus another O2 would make O6. And then for step 3, you would have S2, O, and then there's 6 of them here, plus another 2, so O8. And then the H's, I have H4 And again, this looks wrong, but the order does not matter. And so those would be my activated complexes. All right, go and practice your first introduction to reaction mechanisms.